All right, I think it's recording, right?
I know.
Yo, this guy sucks. I'm gonna keep myself safe. All right. So, hello guys to people on YouTube. Welcome to SystemVerilog workshop. Welcome back.
Come on, bro.
It's over. All right, so today we're gonna go over combination of logic, and then in the second workshop we're gonna do sequential logic. So, because we're doing SystemVerilog, I'm assuming that people know VHDL, they know digital design. So I don't have a slide deck for today. I'm just going to be live coding because you should know what a 2-to-1 mux is before you get here, right? So it's going to be cool, going to be chill. I hope it's like an hour and nothing more because I'm trying to leave. But I'm going to show you some really cool stuff that SV has and the reason why I like it more than VHDL. And I think it's really useful to come from VHDL to SV just so you can appreciate these little things, right? So first we're going to start with the 2-to-1 mux. Actually, before that, I kind of went ahead of myself. So in order to code an SV in the same environment that we did before with Visual Studio Code, I have this extension verified by Dr. Stelele, Teros HDL. You download this. Pretty cool. It's one of the best extensions right now on VS Code. This is the little icon. So once you get the extension, you click this to set it up. All you're going to do, where'd the button go? You're going to scroll down here, I think. Yeah, scroll down here to open global settings. It's going to take you to this. Hold on, Zoom is like
But I'm pretty sure you
on
can hide
top of
that.
it. Huh? Oh, you can hide this?
Like, I can know more. Yeah, no.
Hide
Look,
this?
what do
Wait.
you mean? Maybe.
Aha. Okay. All right, so then you're going to go here. The things that we care about are the formatter and the linter, right? So we're just going to click formatter. We're going to make sure that for the SV formatter, we have variable. And for the linter settings, we have varilator for the linter.
What's lint?
Linter's like, it's like error checking kind of like you go on SV and it like syntax error and also like to make sure you're following general design techniques and stuff. I'm not doing that justice, but that's like what it is. Basic version. Okay. So first we're gonna start with 2-to-1 mux. You guys know what a 2-to-1 mux is, right? So I'm just gonna write it. In SV we have module and module. That's how you write it. This is the name of our module. And then the way we define our port is just parentheses and a semicolon. So in here, we're going to write what our port is, right? A mux has one input, another input, a select line, and an output. So this is kind of similar to VHDL. We don't have to do the standard logic vector anymore. It's just input logic in 0. That's how you do it. So obviously the first line is telling you if it's input or output. The third one is telling you the name, and the one in the middle, logic, that's an example of what type the signal can be. I could be wrong, but logic can be 1, 0, don't care, or Z. I think those are the 4. There's also other ones that will go later, and we'll check it out. This is for SystemVerilog. For Verilog, normally you can just name it wire. Output wire. If you know it's combinational, or reg if you know it's sequential, but logic is just like a catch-all. So we'll go over that later. Anyways, so now we are done with our port. The next thing, in order to define the behavior, we just do it in this module, right here in the space, and that's it. So you can already tell distinctions between VHDL, where VHDL we had an entity, and that's where we defined our port, which is what we have here. And then in architecture, which were separate. But in here, it's just like one thing. Also, one thing to note, unlike VHDL, SV modules can't have multiple architectures. If you want something that to behave differently, you'd have to make a completely new module. You can have multiple modules in the same file as well. Okay, so the first thing we're going to do is we're going to learn the assignment operator. Oh, also, one cool thing to note is comments are now double slashes. So if you're familiar with C++, like it's GOAT. And this also has a lot of similarities with C++, the syntax anyway. We're going to do an assign operator, which is purely combinational. This is similar to in VHDL, like writing a line outside of a process. So we're just going to write assign out, because that's our output. We're going to set it equal to, let's use a ternary operator, so people know what it is. So ternary operator, let's do if select is 1, then out should be in 1, else in 0, right? That's what the ternary operator is saying. So the equivalent of this is just select is our condition. What are these? So a ternary operator can be described of as condition. If the condition is true, then it's the first value, else it's the second value. So that's what we're doing here. So our condition is select equals 1, then it's in 1, else it's in 0. Notice this here. What's up? Yeah, notice this here. This is how we describe values in SystemVerilog. So describing values, we have, what was it again? The width, colon, the type of value, and then the value itself. So 1 colon B1 is equal to width 1. So it's like a 1-bit signal. B is byte, or bit, I mean, sorry. And 1 is, it's either 1 or 0. And also notice like I did cell equals 1 char B1. You guys can tell that this is the equiv operator, like the, if it's true, like comparison. But you can also do in SystemVerilog just could do cell instead of cell equals 1B1. So in VHDL, you have to type it out. In SV, it's assumed, like in C++. And it'll synthesize to the same thing since it's a condition. It'll synthesize to a comparator. Anyways, second one. Mux 2 to 1 if statement. What's that?
So.
Yeah, I should probably write this out. Also, one thing which is cool that takes from C++ as well, or that you see in C++, is the multiple comment, which is cool. Could also do this if select.
You said if this register. Let's check. Oh. Okay, wait.
Does that make sense? All right, cool. All right, so we're going to the second one. I'm gonna get rid of that. This is hurting my, I'm gonna. Okay. Module mux 2 to 1 if. It's the same thing. I'm gonna copy this port. Now I'm gonna show you always com block. Always com, as you can probably tell, stands for always combinational. So anything in here is gonna synthesize to combinational circuit if you follow the synthesis guidelines. process that executes any time the value of a signal inside of it changes. So if you can recall in VHDL, we had process, and then we had to include all the values, all the inputs to our DUT in the sensitivity list. So this would be in 0, in 1, select. The always clomp is equivalent to process all in VHDL. So basically it's just saying that you don't need to specify anything for the sensitivity list, just any signals that you assign here, whenever they change, this always com block will run. So it is pretty cool. So now we're just going to do the same thing I did before, but with an if statement instead of a ternary operator. If select. And also you can do out equals in 0, else out equals in 1. You can also do, notice how we have begin and end in the always com block. I didn't have to use it in this case because this is just one line of code, but say I had more than one line of code, you can write begin and end to pretty much anything. So you do that. I'm just going to keep this here just so you can remember the other part. But yeah, begin and end. Okay. I don't want to write the second if statement module. I'm just going to write a comment here. Alternatively, you can use always star instead of always com. Always is just it's like a process block too, but say you had sequential logic as well, you can mix the two. Always, right with this always block, you can mix comp and sequential if you know what you're doing. And then the star is just saying anything that changes. It's like equivalent to the process all. This would be the sensitivity list in VHDL. This at parentheses, that would be the sensitivity list. And then the star just means everything. What's up?
So what begin?
I'm just telling you that it's like equivalent to brackets in C++. I was just putting the begin and end just to show you that I can.
Oh,
So we can do here just one line, but in case there was multiple lines I wanted to write in the if statement, you have to write the begin and end.
okay.
It just acts like brackets in C++. Okay. I'm going to skip that. Case statement. I think we can do a case later. Okay, moving on. We're going to make a new file. Also, I'm not going to do any simulation at all, just because that'll take more time. And I'm assuming you guys know how to simulate stuff. So the test benches will be provided if you want to do it on your own, but I don't want to be here for a long time. So priority encoder for in. Also, anybody who's paying attention to the SV workshop, I'm assuming you know about Dr. Stitt. I'm just trying to follow the GitHub repository that he has on SV tutorial. I'll post it for anyone that doesn't know. Very useful for VHDL and SV learning. I'll plug it at the end as well, and I'll put it on the Discord just to reiterate its importance. I also check it every now and then because it's really, really good. We're going to make a priority encoder. We're going to make an if statement version. Where'd my mouse go? Here we go. We're going to make our port. If you guys recall, a priority encoder, since it's 4 inputs, in our case, we're just going to make 4 inputs. Notice here that input logic, this would be 1 bit. And since we want 4 bits, we're going to do, we don't need standard logic vector. We just need 2 brackets. Or what's considered not curly brackets, straight brackets. I don't know the difference. Straight brackets, normal brackets? Yeah, whatever. Anyways, Oh, fair. Braces. That's funny. 3 down to 0. So remember in VHDL equivalent to 3 down to 0. You can also do 0 up to 3, but we don't want to do that, right? 0 to 3, whatever. So this is a 4-bit wide signal. Next. Want to make sure we have a valid signal to indicate, yes, this input or this output is valid. And since we have a 4-input priority encoder, we need a 2-bit wide result. Ah. Okay, and we're done with the port. Oh, I just hit my, oh my God. Just hit my shin on the desk. Yeah, that I was trying really hard. Okay. Okay, priority encoder is another combinational circuit, medium scale. So we're going to use always COM again. You need the begin and end for always COM. Remember, for one of the important things in digital design, in order to avoid latches, you want to define the signal in all paths. You guys already know this, I'm assuming. So I'm just going to write valid equals 1. Bro, it came back. The Zoom thing. All right, valid equals 1. And then in a case statement, I'll change it if need be. How do I hide this again? Yeah. Okay, there it is. You can barely see. There's like a really big glare. Okay. So in this statement, to define the priority, you guys remember with VHDL, just if you put the inputs, if you put the most significant first, then that will execute first, etc. So this just synthesizes to a priority encoder. So now that we have a result that is 2 bits wide, now that's why we're doing 2, which is the size of the signal, caret B, we're still in bits, 1, 1. And then we're just gonna continue. I'm gonna go through this a little bit quicker. Uh, right. If input's 1, then it's 1, 0, right? Oh, wait. Yeah, oops. And then, did I do that right? Yeah. And then if input 0, result equals 0, 0. But in case it's anything else, we're going to write our begin because we have more than one line to write. Our valid is not asserted anymore, and then our result will be 0. I keep pressing escape. Die. There we go. And then you can tell that valid is 1 in this path because it's already asserted, and valid is 0 if it gets caught in this else statement. Next. I'm not writing all of that. Oof. I'll write some of it just because we want to see all of the syntax of SV, but I don't want to write all of it. We're gonna make another module. Ugh. Yeah, that's what I was gonna do. No! I keep pressing escape. There we go. All right. This is the first case statement. Should be the same. I'm gonna erase here. We're gonna start with what I just erased actually. Valid is 1. Case statement in SV. Case, end, case. That's the syntax for it. So for our case statement, obviously we want to see what the value is for inputs, right? So that's going to be in the parentheses here. And the way we format this is typically how you'd format in C++ as well. the value of what inputs is, which notice since it's a 4-bit value, the width is 4. I wrote 4 here. We can do a begin and end as well. And we're going to write result equals 0, valid is not asserted anymore. And then you can write another one. Result equals 0 here, etc. I'm not writing all that. Next. Oh, and also you can have a default if you wanted. Okay.
Oh, someone said,
Okay. Moving on. Let's see what else. Oh, I guess we'll just do it here. I'm gonna try to combine all the case modules just so I can show everything that you can do. So the reason why I didn't want to write it is because the specific module that I'm referencing writes all the possible combinations of inputs, right? But another way that you can do it, which is really cool, is you can you can combine some cases to simplify the description. So say, like, for example, 0, 0, 1, 0, since this one is asserted, then we want result to be 0, 1, right? But if this least significant bit is 1, we still want it to be the same value, right? That's how our priority encoder works. So what we can do is write a comma and write that test case, because these two should be the same. So that's one way. And you can do that with as many as you want if you want result to be the same, etc., right? So that'd be better than writing all of them out separately. Another one which is pretty cool, I'm going to copy paste. I'll make case 2. Thought I could do it all here. Wow. There we go. Case 2. I hate everything. Okay, there we go. Specify ranges of values for each case, which is kind of similar to what we touched on just now. But now that we use the inside key or keyword, we can do, I'm just going to skip to one of the ones where it uses it. Actually, I'll do another one actually. One that would cover more stuff. So notice here, if this one is asserted for priority encoder, or for this one, right, we want result to be 1, 1. And no matter what the other values are for the rest of these bits, we still want the result to be 1, 1. So this is basically saying within this range from 1, 0, 0, 0 to 1, 1, 1, 1, all of those values in between, the result should be the same. So that could simplify a lot if you use the inside keyword. And then I will use unique case Z to show both of those. Also, I want to reiterate, I'm not completing all of these. So if you were to test this right now, you'd get some errors because I'm not covering everything. Case 3. So now we're using two things. First, I'm going to write unique before my case statement, and I'm going to change case to case Z. So first thing to note, what case Z does, it allows for wildcard inputs by using a question mark. So say we had 1, 0, 0, 0, like we did here, and like these 3 zeros, you don't care what they are, you want the result to be 1, 1 still, right? Now that we have case Z, we can just write 1, question mark, question mark, question mark, and that covers everything. And then, so that's an example of using case Z, and the unique keyword adds 2 constraints that are checked by both simulation and synthesis. Basically, it's a really nice safety catch for making sure that all paths are defined. So obviously, you guys know what makes a latch. In case you forgot to define a signal in one path, your sim or simulation would fail if you have the unique case. So it's really good for catching those errors. I'm going to write what I just said here. Unique, how do I write this? Makes, make sure a make sure signals are defined on all paths. If not, will throw error in sim and synthesis. I think that's it. If it encounters a case item not covered by the case expression, it'll report an error. It doesn't guarantee that all paths through the case are defined, and it won't guarantee there are no latches, but it's good practice and it will catch those errors. All right. Unique 0. Go skip that one. Okay, next. Now we're gonna make a generic priority encoder. So you guys be introduced to the parameters, right? In case you want to make this modular. So I'm making a new file. So we would define our port as normal. I'll leave these blank because I want to go back to it. And that's it. So in order to make this generic, we need to introduce parameters, which is what I'm about to do right now. So in VHDL, you had the generic keyword, parentheses, and then you define your parameters, right? But in SV, all we have to do is hashtag parentheses, and that's it. So this will be your generic port. So in here, now we can define our parameters. So you're going to write parameter. You're going to specify the type of parameter. I can't recall off the top of my head all of them, but since we only need an integer, we're going to write int. And we're going to write num inputs, the number of inputs we have. In case you had more than one parameter, it's the same as the port. You just separate them by commas, not semicolons. Something else. But we only need one, right? All right. You know the gist. We want to do num inputs -1 down to 0. And then the result, since neighbor. Okay. So since the result is just like a function of how many inputs there are, I'm just going to tell you that you can use log2, which is, that's how you get it. You have $ C log2. That's how you use that. And that'll calculate presynthesis C log2 -1 down to 0. Here you go. And so say we had, say num inputs was 4, it'd be the same thing as the one we made already. 4 -1, which is 3 down to 0. That's 4-bit wide. C log2 of 4, so that's log base 2 of 4, which is just 2. So it'd be 2 -1 down to 0, which is 1 down to 0, which matches the 4 input that we made just now. Just verifying to make sure it works. So this parameter say you wanted to instantiate this somewhere else, you can define what num inputs is, obviously. But say you wanted a parameter that you didn't want to be able to be defined elsewhere. You have like a local parameter. So SV has that too. So these parameters are just limited to the scope of the module, obviously. Local param, that is what it's called. We're going to make num outputs equal to clog2 of num inputs. One other thing that's cool that VHDL does not do is you can make parameters functions of other parameters. In VHDL, I don't think you can do that, right? I think so. Bro, I'm just looking for reassurance, bro. All right. Always com block per usual. For valid, right? Define result. Oh, I defined result everywhere else. For valid equals 1b0. No valid to be 0, right? Same. Are you serious? It's too much of a habit. Okay. And then if we want result to be defined everywhere, we want to initialize it with a default value because I'm not using a case here. We don't know what num inputs could be, so we have to find a way to set all the bits to 0. So we're going to say equivalent, hold on, one more space. To VHDLs, others equals 0. Is that what it is?
Yeah.
Result equals caret 0 done. That's the same, which is really cool. And then now to get started, we're going to use a for loop. No way. For loops, as you know, from DD or VHDL, whatever, it's synthesizable, it just rolls out, right? We're going to define int I, and it has the same syntax as C++, which is really nice. We're going to make our index int I equals num inputs minus 1. Reminder, we want to start at the top because this is a priority encoder. So we want the highest bit asserted to be asserted, right? For a result. I is greater or equal to 0. I minus minus. And then just like brackets in C++, reminder, we need the begin and end, right? If inputs I, which is the current element, equals 1, if it's asserted, we want to begin. You could do result equals I. I should have also said this for this as well. You can do this, valid equals 0, that works, but I like to do this just because I know it reminds me that this is a 1-bit signal, etc. But the 0 would be like a 32-bit int, right? Normally? I think that's right. So that's why I wanted to bring this up here. Result equals I could cause warnings about width, which is why I like to specify this, right? Yeah, I was right. We're storing a 32-bit integer value into an array with fewer bits, which requires truncation. So like, if you don't care about truncation, just do that. But we want to code as best as we can. So some people do this, which is just, or this is how you should do it. This is just saying cast I to the width of num outputs. So now it'll only be as big as the num outputs, right? And then we want valid to be asserted here. And then break. And that is it for our generic priority encoder. And then you could also start from I equals 0 up to num inputs up to num inputs. But that would just be the same thing. You just wouldn't break. You just find which highest bit is asserted. Yeah, I kind of misspoke there. Yes, it would work, but you'd have to check every single bit if you're going from the least significant to most significant. So you wouldn't put a break here. We're just putting a break here since we're going from top to bottom. As soon as we find the first one, then we break. See, I kind of misspoke earlier. Anyways, what else? I think that's it. Oh, local param int. You can also specify the type there. You could also do string parameters as well, which are pretty useful for picking and choosing what you want to, maybe what type of circuit you want to synthesize to. I think we're going to do add, multiply, and that's it. I think that covers combinational. We're going to move on to adder. Okay. We have our generic, which we discussed just now. Parameter width, and then we're going to define our port as well. Yeah. And our size, our generic size with -1 down to 0. Oh, backspace, where'd you go? Wow. And then this is the sum up. All right, so since this adder in particular, we're not worried about a carry in or a carry out. If you remember in VHDL, we had, what is it, numeric standard package. We had to cast it to unsigned, add them, then cast the whole thing to standard logic vector to make sure it matches our port. And in SV, we just, since it's combinational, we use an assign. Sum equals in 0 plus in 1 done. That's it, which is really convenient and cool. And yeah, we're going to cover that right now. But that is it, which is really nice. You don't have to cast anything. And let's say there was a carryout, because that would definitely happen, right? Michael brings up a good point. We're going to do output logic carry out. I'm going to change this to, say, carry out. So if you recall, when we made a local param, that was a local parameter limited to the scope of the current module that you're in. You can also make internal variables, which you guys have seen in VHDL as well. Signals that are limited to the scope of an architecture, and a variable that's limited to the scope of a process. So this is going to be limited to the scope of our module. Logic with -1 down to 0. Full sum. Or width down to 0. Because we want to count to for the carry out, right? Let's see.
Just
Yeah, you're right. Which is why I put width to 0. Because then the most significant bit from full sum will be the carry out, and then the rest will be sum.
you just define, can't you just define topics, carry out plus sign?
Yes, you could. You could as well. All right, so the next example covers non-blocking, which I'm just going to leave for sequential logic, because I just want to make this as simple as possible. All right, we need an always com block, so we're going to start that near begin. So let's say in 0 and in 1 were their max value, it would overflow. So say we wanted to assign 2 more intermediate signals here, full sum, like in 0 and in 1, where they were like width down to 0 as well. In SystemVerilog, it makes it really easy to concatenate, so we don't need to do that. We're going to assign full sum with curly brackets this time. like this, this is saying in zero concatenated with a zero in the front of it. We're going to do the same thing for in one. So now they are essentially, or full sum is being assigned uh, with down to zero in zero and with down to zero in one, which is really nice. So yeah, equivalent to the ampersand in VHDL of zero to the front of in zero and in one. And then just like we said before, sum will just be the just with minus one down to zero of full sum. So we're just gonna slice into that. And then for the carryout, we just have the most significant bit of full sum, right? And we're done. Another way to do it, which is really nice, I'm going to copy the module I just did. I'm going to change this to carryout one, carryout two. If you want it to be contained in just an assign operator, which is pretty funny, we do assign. This is another use of the curly brackets. There's actually so many that it gets kind of overwhelming at this point, but this is equivalent to the module we just made in add carryout one. If you have the curly brackets on the left side, it will not concatenate, it'll just assign the overflow bit. Yeah, so let me write that just so we instead use concat on the left-hand side, and SV chooses the width of an operation based on max of operand widths and result width. So since the result is one bit wider than the sum, SV will automatically zero extend the operands to match. So that is equivalent, which is really cool. Let's see. And then we can do the same thing we did here with a carry in if we wanted. We would just add, I'll just do that right now actually. In case we wanted to carry in here, all we would have to do is this, and that's it. So now we have a carry in. Let's go to, let's see what else. Let's go to multiplier. And this will be the last module we do. I think I don't think we should cover an ALU because I'm assuming you've made an ALU in VHDL. I think this is more to like reinforce the syntax of SV and to learn the differences, right? So this will be the last one. Mult 1, you can probably tell already that all this really cool operators and syntax from the adder are going to be used for the multiplier as well. We don't need to cast anything like we did in VHDL. So it'll make this way easier and less lines of code. We're going to have a second parameter. We're going to make it of type logic. And we're going to assign is signed. And we're going to assign a default value. Because for our multiplier in particular, let's say we wanted to do assigned and unsigned multiplication. This parameter will tell us, well, which one do we want to do, right? Input logic, input with -1 down to 0. You know the drill. Copilot, it's hilarious.
Turned it off.
That is very funny.
Eating.
You're cheating, bro. And then you guys know that if we're multiplying in 0 and in 1, the result will be double of what their widths are, right? So that's why I have input times 2 minus 1. You guys know this. Always com block once more. So now we're going to do an if statement with our parameter is signed. And depending on what the value of is signed is, then we'll do either signed or unsigned multiplication. And then I'll just do this here. Why is it doing this? All right. So what I want to note here, SV arithmetic is unsigned by default. So if we want to do signed mult, we have to cast it to signed. So for this first one, if is signed is asserted, we want the product to be signed. So we're just going to do product equals, this is how you cast it to signed. And then else we just want a standard unsigned, right? So it would just be in0 times in1 done. That's it. Let's see. Okay. That should be good. What else? Oh, this is an example of, hey, what if I don't want to use an always com block? I want to be different. This is mult2. And delete this. This is introducing a generate statement. So using generate and if statement instead of always block. The generate and end generate is apparently optional according to the language definition, because any time SV detects an if foreign case statement, they should be automatically detected as a generate block, which is kind of cool. I didn't know that. But just to make sure you're covering like all your bases, and maybe some tools don't support that, we're going to use generate block. Assuming you guys know what generate is from VHDL. And generate seriously. All right. Is signed. We're gonna do the same thing we did just now. We're gonna do our begin and end just to show you some differences. And else begin end. And then one thing to note, anytime you have an if statement, a for loop, an always block, I think, you can do a semi or colon and write I'm blanking so hard. A label, write a label. So a label is signed. So anytime you're like simulating or whatever, and you want to make sure like where is this? Like where is this? Why is it getting assigned like this? You can see in the simulator, this is the block that you're running because it has a label on it. So it's useful if you have like a lot of stuff and it's really hard to keep track of everything. That'd be really good for catching stuff. In this if statement, we're just going to use the assign operator since we're trying to effectively replace the always com block, right? So I'm just going to write the same thing I wrote before. Done. Okay, I think I'm going to do 2 more. Wait, apply. I'll do 1 more. All right. I'm gonna copy this one. Alt 3. I won't change only 3. Alt high low. This is, you guys have probably seen this before. Say we want, instead of capturing input with times 2 minus 1 down to 0 for product, maybe we just want the high and the low half. So it should be the same size. And same for low. And then, as I said just now, even for always blocks, you can write a label. So that's going to be our label for the always com block. One thing that we haven't done, which is pretty cool, is you remember when I told you that you can define a signal within the scope of your module, like how we did it in here? Oh, times 2 minus 1 down to 0. You can also limit it to the scope of your always block. And this will be useful as shown later, maybe another workshop. Now it's only limited to the scope of this always com block. So this doesn't exist outside of it. And that's why maybe a label would be important here, because if you didn't have a label, you couldn't even see what the value was of the product since it's inside this com block. Or sorry, the simulator might give this another name and you won't know if it's this that it's referencing unless you have a label. I don't want to write it again. The same thing we did. Where is it? Here, right? Same thing we've done before. Just gonna write it here. And since we want to splice into this like width times 2 product, we have to assign high and low. And then I will kind of mix a com block and an assign block just to show you that you can do that. We could write it in here in this com block, but I just want to mix it to show you that it's exactly the same. Assign high equal to product, but only from the top half.
Product still.
Oh, you're right. I can't even do that. You're right. If product is defined here, then this won't work. Thanks for the catch. Yeah. Yeah, you're one step ahead. If product was outside the always block, you can define high and low out here with an assert or assign.
Are there any advantages?
Not really. I was just trying to show you that you can mix both of them, since this assign line and always com will be the same because they're both combinational, right? But yeah, there's no advantage unless you want to write it that way. What? Yeah, up to preference. But if say you had like a lot of combinational stuff, you wouldn't want to do assign. That'd be like 40 whatever assigns. Always com, you wouldn't have to write assign all the time. Anyway, so the high is just slicing product from the highest bit to halfway, which is input width, and then low equals the product of input width minus 1 down to 0. And we are done. That's it for SV. Go get a job. Oh, thanks. Okay, and then one other thing to note as well. This was all combinational. Our next workshop will be sequential. Obviously, we can't run through everything from Stitch tutorial because that'll take a lifetime. I just want people to get started on like this was like a good intro to the syntax, how to write combinational logic. If you want to go more in depth, there's a lot of things that I skipped that he doesn't on the repo that I will link in our chat. So I hope you found this useful, and I'll see you guys later. See you guys in the next one.